Okay, so we have to consider then the effect of geometry on aggregation. And in particular, we want to think about when these amphiphils clump into aggregates, how is the bonding changing? So first we need to characterize something about the bonding. So let's characterize the energy associated with bonding. And we know that in an amphiphilic system, this is typically approximately the same as the energy associated with thermal fluctuations. So, and here we're not saying that the energy of bonding depends on the temperature. We're just saying the energy of bonding is on a similar energy scale to kT. And we're going to say the energy of a bond, let's denote a typical bonding energy as minus alpha kBt. That is, that it's we're going to just take some constant alpha and say that that's the ratio between the bond energy, the energy by which the energy is lowered, the ratio between the amount the energy is lowered by making a bond to the energy of thermal fluctuations. So, if alpha is much less than 1, then bonding is on a scale less than kT, right? And if alpha is much greater than 1, then the bonding is on a scale more than kBt. And if kBt is room temperature, then this would typically be the case for metals, but for amphiphils, alpha would typically be somewhere around 1. Okay, so now let's think about different bonding geometries. So let's first consider the linear chain. Okay, so here we have a bunch of amphiphils, and let's say they've all lined up into some kind of linear chain. Okay. So each molecule here has 2 bonds. So this molecule shares 2 bonds with neighbors, right? And so it lowers its energy by alpha, or minus alpha kBt, right? So it has 2 bonds, so 2 alpha kBt, but each of those is shared between 2 molecules, so they're minus alpha kBt per molecule. And then you have an end molecule, right? This molecule has only half that contribution. So that molecule has an energy minus alpha over 2 kBt, right? So if we were to look at the total energy associated with all those bonds, that would be equal to n times mu n0 by definition. That is, each molecule is being assigned some amount of energy that it's getting from the bonds, and that would be minus n over 2 for the number of molecules that are in the middle of the chain, or minus n minus 2, right, times alpha kBt, right, and then minus 2 molecules that each have half alpha kBt, so minus alpha kBt. Right? So the total here would be minus n minus 1 alpha kBt. So we can rewrite this then as that mu n0 is equal to minus alpha n kbt, right, plus alpha kbt all over n, so that's minus alpha kbt plus alpha over n kbt. Okay, so what does this tell us? Well, this term is the term we'd get if we just had an infinite sized aggregate. That is, the chain was so long that the ends didn't matter. So this is what we'll call mu infinity, mu 0 infinity. So this is energy in an infinite sized aggregate. But then there's a correction which is due to the ends. And so another way of writing this is to say that mu n0 is equal to mu infinity 0. That is, the energy the molecule would have if the aggregate got infinitely large, plus alpha kbt over n. Okay, and this should hold for any rod-like, so this is for rod-like, any rod-like structure, any one-dimensional structure would have that basic scaling. Now, what if we had something that wasn't rod-like? What if it was a disk, right? So how about disks? Okay, well, in that case, we're creating some kind of structure, like a two-dimensional structure, like a raft. And we're saying that the internal molecules have energy equal to minus alpha kbt each, but the ones on the edge have half that, minus alpha over 2 kbt. And so then if we were to try to write down an energy for the whole system, we have to know how many are on the edge of the raft versus how many are in the middle of the raft. So the number on the edge would be proportional to the circumference, right? 2 pi r r0, let's say where r0 is the radius of a molecule, over pi r squared. So that would be the fraction, so this would be 2 pi r squared divided by pi r squared, so where this is the total area, right? And then the number, the total number would be pi r squared over pi little r naught squared. That's the size of the molecule again, right? So the number on the edge, or the fraction on the edge, is going to be proportional to 2 r naught over r. So the number on the edge, or the fraction on the edge, is going to be proportional to 2 over square root of n, because we know the total number is proportional to 1, is proportional to r over r naught squared, right? So r naught over r is equal to square root, or 1 over square root of n. Okay. So we get that the number on the edge goes like 2 over square root of n. So for a disk, we get that mu n0 is equal to mu infinity 0, what we would have for an infinite cluster, plus alpha kbt over n to the 1/2. This is for disk-like aggregates. So we can see a trend here. So what if we had clumps So the third case would be, how about spheres? In that case, the number on the surface, if we reasoned it out similarly, we would get mu n0 equals mu infinity 0, and we'd get plus alpha over kbt, and the fraction on the surface would go like n to the 1/3. So this is sphere-like. So our general result is that we always get some solution that looks like mu infinity 0 plus alpha kbt times n to some power, where the power depends on geometry. Okay, and that's going to be useful for us for analyzing